This is the third video of the compressible flow chapter. We're going to learn another important reference state called the critical state and also study shock waves. Similar to the stagnation state, critical state is another reference state used frequently in solving compressible flow problems. It is the state where the Mach number is unity and shown with the superscript star. It is quite possible that the Mach number of unity is not achieved anywhere in a duct flow. It means that the critical state does not really exist in the problem. But even in that case, we can still make use of the critical state in our calculations. And when an actual critical state exists, it is seen where the area is minimum, which can be the throat of a converging-diverging duct. The equations seen in the left box are the ones derived earlier in slide 421. They are the ratios of the stagnation state properties to the properties of any other state. If we set the Mach number to 1, we get equations for the ratios of stagnation state properties to those of the critical state. The first exercise in this slide asks for the derivation of an equation for the area ratio A over A star. We use this equation to get a link between the geometry of the duct and physical properties in it, such as the Mach number. The question we want to answer is, can we find the area of a section if the Mach number there is known, or vice versa? For example, many times in solving problems, the throat area is a known parameter or a parameter that needs to be calculated, which makes this area ratio useful. Derivation of this equation is given in your textbook. This rather complicated equation looks pretty simple when plotted, as you see here. This plot is generated for air, and the horizontal axis is the Mach number. The area ratio is equal to 1 at Mach number 1 as expected, and it is greater than 1 for all other Mach numbers. This confirms that in an isentropic flow, Mach number can be 1 only at the minimum area. If the Mach number at a section is known, it is straightforward to get the corresponding area ratio. For example, if the Mach number at a section is equal to 2, the area of that section should be about 1.7 times the critical area. If, on the other hand, the area ratio is known, there are two corresponding Mach numbers. For example, for a section with the area ratio of 1.5, the Mach number can either be about 0.4 or 1.8. One of these is subsonic and the other is supersonic. Only one of them can be true, and the correct one should be determined by considering the physics of the flow. The second exercise in this slide is about the derivation of an equation for a non-dimensional mass flow rate parameter, which is used frequently in solving problems. This parameter combines the mass flow rate at a section and the area of that section with the stagnation temperature and pressure. Although not given here, the result is again a function of Mach number and the specific heat ratio. You can find the result and the detailed derivation in your textbook. Here is the plotted version of this parameter. Horizontal axis is again the Mach number. 3 different curves are provided for 3 different gases. The most important detail in this plot is that the maximum value is obtained at Mach number 1. For a given gas, such as air, the maximum value in the plot is 0.6847. Equating the expression that is plotted to this maximum value, we get an equation for the maximum possible mass flow rate that can pass through a given duct with some fixed stagnation properties. This maximum mass flow rate is obtained when the Mach number is 1 at the minimum area. It is not possible to increase the mass flow rate any further without changing the stagnation properties or the duct geometry. This condition, when the maximum possible mass flow rate is achieved, is known as choking, which is an important and somewhat puzzling detail of compressible flows. We will talk more about it later. Up to this point, we've seen many equations for isentropic flows inside ducts. They were all functions of Mach number and specific heat ratio. The equations were nonlinear and they are not easy to use to solve problems. Plotting the equations for certain specific heat ratios and using the plots in solving problems is easier than using the equations, however, this brings reading errors. Another alternative is to tabulate the data, such as the one shown here. This table is created for air with K being 1.4. Similar ones can be generated for other gases with different K values. The first column is the Mach number, shown with letter M. It starts from 0 and increases up to 3. Actually, this table is long, and here we see only the beginning of it. For each Mach number, several parameters are listed, such as P over P0, T over T0, rho over rho 0, A over A star, and the non-dimensional mass flow rate that we studied in the previous slide. In the sixth column, there is the I over I star ratio that we haven't discussed. It is the impulse ratio, and we are not going to use it in our course. We will refer to this isentropic flow table as Appendix C3 because it is taken from Appendix C3 of Professor Axel's textbook. A similar table also exists in the appendix of Munson's book as Table D1, part of which is shown here. But the Mach number increments in this one is too large and the non-dimensional mass flow rate column is missing. Therefore, we will be using Appendix C3 table of Axel's book, which is available at cont'd class. Please download it and make yourself familiar with it. In this slide and the next one, there are 3 exercises about isentropic duct flows. Solutions of 2 of them are given in the solved examples handout. Please study them and solve the remaining one by yourself. In this slide, we will introduce shock waves, which are interesting features of compressible flows. Shock waves are called strong waves because unlike a weak sound wave, across which properties change only by infinitesimal amounts, properties change across a shock wave by finite amounts. At a very small distance, such as 1/10 of a micron, the flow properties, such as speed, density, pressure, or temperature, experience jumps, almost as discontinuities. Shock waves can be stationary or moving. They can be normal to the flow, that is perpendicular, or they can be oblique, making an angle with the flow. In this course, we will study stationary, normal shock waves seen in one-dimensional duct flows. A shock wave can be seen when the conditions are appropriate. It is a physical mechanism that a flow should go through in order to adjust itself to some specified downstream conditions. Consider a supersonic flow where the fluid moves faster than the sound. It is so fast that it may not be able to adjust itself to what happens downstream, such as an obstacle located ahead for an external flow or a fixed outlet pressure for an internal duct flow. When the fluid particles have no chance to adjust themselves to such conditions, they may be forced to go through a very sudden change, which is a shock wave. Let's make an analogy about this and a very fast-moving traffic. Consider that cars are moving on a road very fast and there is a downstream condition ahead, such as a red traffic light. The light is behind a corner, so the cars are not aware of it. As they turn the corner, they see the light and try to stop. But they are so fast, there is no time to react properly, and they all crash into each other, causing a pile-up. This pile-up is not the same as a shock wave, but the analogy helps to put things into perspective. Shock waves are not seen in incompressible flows, because in such flows information travels at infinite speed, that is, the speed of sound is infinite. No matter how fast the fluid particles are, They can always get the information about the downstream conditions ahead of them in a timely manner and can find time to adjust themselves without needing to go through a shock wave. The traffic analogy for this is to have cars that can all react to the red traffic light simultaneously. When the first car that turns the corner and sees the red light decelerates and stops, this information propagates backwards at infinite speed, and all other cars can show the same reaction simultaneously. This way the accident can be avoided. We can say that this is an idealized incompressible traffic. The cars which model the fluid particles do not compress. They can always maintain the same distance between them. In designing roads and controlling the traffic, the term traffic shock wave is sometimes used. It is about the unexpected pileup of cars in a traffic that was just flowing normal a few seconds ago. Let's watch a short video about it. Watch the upwards going traffic and try to notice how the cars pile up suddenly without no apparent reason. They come to a complete stop and then the traffic goes back to its normal flow. This is maybe because one of the drivers slowed down unexpectedly or changed lane unexpectedly. But the cars here are not that fast. They have the time to react properly and avoid an accident. Here we see some shock wave photographs. They are seen in these images as black lines. The first one is the oblique shock wave attached to the pointed nose of a supersonic bullet. This is an oblique shock because the flow passing through it is not normal to it. The second one is the detached bow shock seen ahead of a blunt-nosed object moving at a supersonic speed. This object looks like to be a model of a lander module of a space mission, maybe to the moon or maybe to Mars. The last one is a normal shock wave photographed inside a supersonic duct. The extra oblique waves seen are created by surface roughness. Shock waves can be visualized in laboratory using a number of different techniques, such as Schlieren photography. This technique makes the sudden density changes across a shock visible. Let's watch two videos about Schlieren visualization. The first one is not about shock waves actually. It is about lighting of a matchstick and visualizing the density gradients it generates. The second one is about the shock waves generated by a supersonic bullet. Both videos are actually longer than the clips that I'm going to show you, and you are advised to visit the links in the description to watch them in full.
So when you watch the lighting of this match, you're seeing heat generated from friction, igniting phosphorus, which in turn generates more heat and begins the reaction between sulfur and potassium chlorate, which releases sulfur dioxide, which you can also see. And you can see my breath as I blow out the flame.
And this one is a CFD simulation of the Mach 1.6 flow over a blunt-nosed bullet. Formation of the bow shock ahead of the bullet can be seen clearly. This slide and the next one are about how a strong shock wave is formed by the accumulation of a series of weak compression waves. I'm gonna skip them in this video, and you can also skip them in your own reading. Here we see a stationary normal shock wave inside a duct. The states just before and just after the shock are shown with the letters X and Y respectively. The sudden and finite changes across a shock wave make the flow across it non-isentropic. but the shock is so thin that it has negligible heat transfer with the surroundings, and the flow across it can still be considered as adiabatic. For a duct flow with a normal shock wave, there are two isentropic flow regions, one before the shock and one after the shock, and these regions are separated by a very thin non-isentropic region between them. There are two different stagnation states shown with subscript 0x and 0y. They are the stagnation states of the isentropic flows before and after the shock. The properties such as pressures and densities of these two stagnation states are different. But since the whole flow is adiabatic, including the shock, stagnation temperature and the stagnation enthalpy are still unique. It is important to understand this detail. In this slide, we are emphasizing the fact that a flow with a shock has two different stagnation states. The flow inside the shown duct has a shock wave. Normal shocks inside ducts are typically shown with wiggly lines. State 1 is upstream of the shock, and state 2 is downstream of it. If we take the fluid at state 1 and isentropically decelerate it to 0 speed, we arrive at the stagnation state shown here with subscript 01. It can also be called the state 0x, meaning that it is the stagnation state of the flow before the shock. If we do a similar isentropic deceleration for state 2, we arrive at the stagnation state shown with subscript 02, which can also be called the state 0y. As shown, the pressures and densities of these two stagnation states are different, but the enthalpies and the temperatures are the same. This is how the non-isentropic process across a shock wave is seen on the TS diagram. X and Y are the states just before and just after the shock. On the TS diagram, there are two different points. We know that the temperature increases across the shock, and that's why point Y is located higher than point X. Pressure also increases across the shock. The process is non-isentropic, causing entropy increase. State Y has higher entropy than state X. As seen, both states have the same stagnation temperature, but their stagnation pressures are different. In order to be able to solve problems with shock waves, we need to formulate the changes across it. For this, we can take a control volume between states X and Y and write the mass, momentum, and energy conservation equations. On this slide, we only show the beginning of the mathematical work. If we continue with the details of this process, which can be found in your textbook, we can come up with the equations for the ratios of properties across the shock, such as the pressure ratio Py over Px. Results of this derivation are shown in the next slide. The equations shown here are for the normal shock wave of a perfect gas. Given the Mach number, max, before the shock, we can first calculate the Mach number after the shock, may. Then we can calculate property ratios such as Ty over Tx, Py over Px, ρy over ρx, Vy over Vx, and similar ones shown on the next slide. Note that these ratios are all functions of the Mach number before the shock and the specific heat ratio. These are the remaining normal shock wave relations. Here we see the P0y over P0x ratio and the A star y over A star x ratio. It is important to note one more time that the stagnation pressures before and after the shock are different. As seen here, the critical areas, the A stars, are also different. The final relation is for the change in entropy across the shock wave. Similar to the isentropic flow table that we use in solving problems, the equations we've seen in the previous two slides are also tabulated. This table, called Appendix C4, is again taken from Professor Axel's book. It is the normal shock wave table for air. Its first two columns are for the Mach number before and after the shock. As you see, the first column starts from Mach number 1, because the flow before the shock must be supersonic. This restriction is due to the second law of thermodynamics, details of which can be found in your textbook. And as you see in the second column, the flow after the shock becomes subsonic. So always, a normal shock wave converts a supersonic flow into subsonic. The other columns are for the pressure ratio across the shock, temperature ratio, density ratio, which is the reciprocal of the velocity ratio, stagnation pressure ratio, which is the reciprocal of the critical area ratio, and the non-dimensional entropy change. Please get familiar with this table. This is the plotted version of the normal shock relations. This plot is generated for air, therefore it delivers the same information as the table of the previous slide. It is easier to understand the changes across a shock in this plot. The horizontal axis is the Mach number before the shock. It starts from 1, where all the ratios are equal to 1. As the Mach number before the shock wave increases, the shock becomes stronger, meaning that the property changes across it become higher. It is important to know which properties decrease and which ones increase across a normal shock. As seen in the graph, Mach number, velocity, and stagnation pressure decrease across a shock. On the other hand, pressure, temperature, density, critical area, and entropy increase. Stagnation temperature and the stagnation enthalpy, which is not shown here, remain constant. While solving problems, if you need to remember which properties increase and which ones decrease, you can easily understand it by looking at the numbers of the Appendix C4 table. This exercise is about the shock wave formed in front of a pitot tube inserted into a supersonic flow. This may be the pitot tube of a supersonic fighter aircraft. This is a solved example in Munson's book. And here we have two more exercises involving shock waves. You can find a solution of the second one in the solved examples handout. Please try to solve the other one by yourself. This is the end of the third video of the compressible flow chapter.